Now we discuss the details related with the phase diagram. As you know, yesterday we already discussed there is a solid here, liquid, vapor, and gas. The difference between vapor and gas is located in this area. This point C is critical point. Oh, the line is not so good. I will erase this one and then put better line. I haven't recorded yet, right? You already record. Okay, thank you. Okay, so this is the line. So in this case, this point is critical temperature. Similarly, you can draw the line to the left, and this point is critical pressure. What is so important about critical pressure and critical temperature? You remember last class we discussed about this ideal gas, and this is the condition. The operating pressure is much lower than critical pressure, while the operating temperature is much higher than critical temperature. So, based on this condition, can you predict where is the location of ideal gas? Is it in the top right corner, top left corner, bottom left corner, or bottom right corner? Remember the ideal gas condition. Temperature is higher than critical temperature, while the pressure is much lower than critical pressure. Come on, can you help me? Where is the location of ideal gas?
Bottom right.
Yes.
Sir.
On the right, bottom right corner. Okay. This is the location of ideal gas. So, the formula that we know, EV is equal to nRT, is actually only valid when the system located in this ideal gas region. Unfortunately, in the real case, the one that you can find in the process plant, in the process industry, most of the time located in this area, not in the ideal gas condition. In fact, even though if the phase is in a gas state, the location is not so close to ideal gas. Normally, the area is in this region, close to critical temperature or critical pressure, or sometimes with the pressure close to critical pressure instead of very low pressure. That is the condition. Okay, so now you understand where the ideal gas can be used for calculation. It's true. It is true that this one is very simple formula, but there is term and condition. It's only applicable when the system is reached. Okay, and the remaining one I will not discuss in detail. We will discuss in a separate section later on in vapor-liquid equilibrium. In this slide, I just want to emphasize the location of ideal gas. Sometimes when you have a problem and then it's considered as ideal gas, the location should be somewhere in the bottom right corner of PT diagram. Remember last class I also discussed the condition of air in our atmosphere. 1 atmosphere compared to critical pressure of oxygen and nitrogen. It is much lower. Similarly, 25 degrees C or 298 Kelvin, it is much higher than critical temperature for oxygen and nitrogen. Okay, that's why we can consider air in this atmospheric condition as ideal gas. Okay, you remember that air consists of oxygen and nitrogen, right? 21% and 79%. In room temperature, this is 25 degrees C, and ambient atmosphere, this is atmospheric, it's around 1 bar. We can consider air as ideal gas. So what is the advantage of ideal gas? Let's move to this part. When we consider an ideal gas, internal energy and enthalpy is only a function of temperature, like Pak Sanggono explained during the last class. That actually enthalpy is also a function of pressure. But because we consider as ideal gas, we can eliminate or neglect the effect of pressure. So the enthalpy is only a function of temperature. We will learn later on, or maybe tomorrow, that this one is equal to mCv delta T, while enthalpy is equal to mCp delta T. Even though Pak Sanggono already discussed in the last class. Okay, another advantage of ideal gas, you can remember this one. In a real case, the ideal gas does not exist. What does it mean? It means that the enthalpy that only influenced by temperature is not exist. But the gas that have low pressure or a very high temperature can be said to be close to ideal gas. And the property of this ideal gas is very useful for early evaluation because of this simple formula. Later you will learn how to calculate real gas using real gas equation of state, not the simple ideal gas formula. PV is equal to nRT. Okay? Okay. And this is the last one related with ideal gas. Again, all of the properties is independent of pressure and volume. It's only depend on temperature. Okay, most of the time for undergraduate student, we will discuss using ideal gas assumption. But some of the certain cases, at least you know how to calculate using real gas equation. Okay, up to this point, any question? No, still simple, right? Now, the next one, I want to discuss why we have the previous calculation in your quiz related with Joule experiment. Okay. The original of delta U equal to Q plus W is coming from Joule's experiment. This experiment is very simple. So because you already have this kind of quiz, it should be easier for you to understand. The first step from Joule's experiment is preparing a vessel containing water on it. So there is a water inside this vessel, and he put a propeller inside it, like this, and he used thermal insulation. This is the first condition. The tank is isolated. First, he checked in the first or initial condition. This is initial. Joule and the team check the temperature between the system and the environment, the surrounding. And if you check here, the temperature is the same. The system temperature is equal to environment or surrounding temperature, even though it's already isolated. That is the initial condition. The second step, what he did is he tried to put a work on the system using this impeller. So he stirred the water continuously, and he checked a different temperature inside the system. And he saw that the temperature rise up to a certain point. So in the second condition, this T system is increasing from T0, let's say, to T final. Okay, this is the condition. This T final is higher than T environment, the surrounding temperature. After that, Joule and his team stopped the work. So he stopped this impeller. So no more work given to the system. It is given to the system. No. But the temperature remained the same. The temperature can be held in T prime. Okay. The third step. What he did is he opened the thermal insulation and again check the temperature. And this temperature started to decrease until it reached the initial condition where the temperature of the system is equal to ambient temperature. So this third condition, the temperature of the system went down and reached the initial temperature. I will put it here as T0. Okay, this is T0. Okay, based on this simple experiment, Joule he proposed a relationship where the energy can move from one to another. The first one, when he put the work towards the system, it means there is additional work that can be given to the system. What happened here, this step, work in is equal to an increase in temperature. So he mentioned that there is an increase in internal energy. Why internal energy can be increased? Remember last time we already discussed about this in a different chapter. Internal energy is a function of molecular movement. You remember there is translation and then rotation and vibration. Okay, please check again the previous chapter, the previous slides. What happened to translation, rotation, and vibration when you give additional energy, even though it's not heat, the energy can be work as well. The molecular movement, whether translation, rotation, or vibration, increase, and it will be stored inside the system. In this case, the water as a fluid. That's why an increase in temperature can be observed. Okay. Please also remember this translation, rotation, and vibration. Translation movement is, let's say you have a monoatomic molecule like helium, argon, and so on. The dominant movement is translation because it's like a ball. The effect of rotation and vibration is not significant compared with translation. But when you have diatomic molecules like oxygen or nitrogen, the shape of oxygen is like this, while the shape of nitrogen, we have triple bond like this. Okay, so not only translation, but also rotation. Later on, you can understand why there is a difference in terms of internal energy. It's really depends on the type of molecule. In this example, the fluid itself is water. So not only translation and rotation, but also vibration. Because the shape of the water in molecular structure is like this. Hydrogen to oxygen and again to hydrogen with a certain degree, around 108 degree. Because of different atomic size between hydrogen and oxygen, the bonding have additional movement. We know this one as vibration. So in the case of water, all molecular movement, translation, rotation, and vibration contribute to internal energy. That's why an increase in temperature can be seen relatively easy compared with only helium or argon or only oxygen and nitrogen. Okay, up to this point, any question? If not, let's go to the third state. In the third state, we Joule open the thermal insulation. What happened to the case? The heat come out from the system to the environment. So heat go to a different direction outside the system, like you can see here. And the effect is a decrease in temperature. So there is a difference in delta U. Sorry. Okay, so step by step you can see this one. And as a whole, Joule proposed that delta U is a function of heat and work. And remember, during your last quiz, all in terms of sign convention, all energy direction that going into the system, it can be heat absorption or work done to the system, you need to put positive sign. Okay, and the opposite way, if you have an energy coming out from the system, it's like system done the work to the environment or the heat released from the system, you need to put negative sign. Okay, so now you remember how, or you can understand more details related with the Joule experiment. Any question up to this point? No? If not, let's go into a detail about this. Remember, the internal energy can be kinetic, potential, or the rotational energy of the molecule itself. Okay, the one that I want to add related with internal energy, because this is the most important part. The amount of internal energy cannot be known with certainty. So we don't know the absolute number of internal energy. That's why we always put it as delta. Remember delta U, let's say delta U12 is equal to U2 minus U1. It's always a delta, a difference between final state to the initial state. And please remember that internal energy is also state function, one of the state function. It's not depend on the direction or in the pathway. As long as you know the initial state and the final state, you can consider the calculation as state function. The one that I want to give you, this is like intermezzo, but it will be better if you understand this. Why we cannot know the exact value of internal energy? Maybe you know Kelvin. His name used to be one of the famous unit for the absolute temperature. What he did is he plot several gas at that time, it's not so many, from helium, argon, oxygen, nitrogen, and so on. He plot its activity as a function of temperature. And he found out that all of this he tried to put extrapolation for all this kind of activity, and it reached a certain point, where at this point he considered that the activity is close to zero. So he considered at that point, based on calculation for sure, because this one is extrapolation, the real data that he plot is only relatively high temperature, even though it's a minus degree C, but still much higher compared to the real activity where all of these molecules become freezing, stop. Even ice itself still consists of molecular movement. The water molecule inside ice is still moving. But Kelvin went beyond that one. He predicted that at a certain temperature, all the molecules will stop. No more translation, it cannot move. No rotation, the molecule will stop, will not rotate. And no vibration. And he claimed this one as absolute temperature. Further on, the researcher who follow his idea consider this one as 0 Kelvin. This is the absolute temperature where the molecule stop moving. So no more translation, no more vibration or rotation. But again, it cannot be proved because there is no device that can reach 0 Kelvin, and it's very difficult to prove this concept. But all researchers who works on thermodynamics agree with this point. Okay, this one is 0 Kelvin, not okay. Okay, so because of that, the real value of internal energy cannot be proven. It still have a lot of uncertainty. This is the main reason, because there is no validation of it. To validate the model, we need real experiment, right? This is important for doctoral student like Shad. If you propose a model, particularly related with thermodynamics, once your model is constructed, you have to make sure it works, right? Before of that, make sure you do a verification or validation related with your model. Similarly with Kelvin. You cannot prove this one, but all of thermodynamic enthusiasts, thermodynamic researcher agree with his proposed model. That is one of the reasons why internal energy, the real value of internal energy cannot be used as a, there is no real proof for the value of internal energy. But there is no issue if we consider as a delta. We can put, let's say, a certain condition here where we can validate as a reference. So the real reference for internal energy is 0 Kelvin, but we can put additional reference here. This is reference temperature. And all the internal energy will be compared to this value. That is one of the reasons you cannot find the real U number, always delta. Okay, that is a special case for internal energy. Okay, internal energy of an object, often in absolute term, is 0. Some of the book mention it as ground state. But again, it's only based on extrapolation. There is no proof that at 0 Kelvin, all the activity will stop. Okay, that one is internal energy. Now, the first law of thermodynamics, you still remember that we consider as law of conservation of energy. And remember, in Joule experiment, we can also consider like this. Delta U is equal to Q plus W, where delta U is U2 minus U1. This is the one that we already discussed previously. Also remember the sign convention. Positive is coming to the system. Negative is leaving the system. I will skip this one. Okay. Remember the first part when Joule put thermal insulation. When thermal insulation occurs, it means there is no heat go into the system or release from the system. But Joule put energy in terms of work using impeller. And there is an increase in temperature. That's why we have this condition. Okay, as long as we can make a perfectly thermal insulation tank, this one is okay. Now, the second one, we stop the work, Joule stop the work, and then start to open the thermal insulation. What happened? The temperature decreased from higher temperature to ambient temperature. So no more work, but the heat released to the environment. Remember the negative sign because it released to the environment. Okay. Now, because of the system reached the original state, remember the cycle concept. Let's say delta U is 1, 2, 3, and return to 1. This one absolutely 0. We can make sure that the value would be 0 because it is a cycle. Remember our last quiz? You have 4, right, at that time? 1, 2, 3, 4, and then return to 1. This value should be equal to 0. So, when the temperature return to the original temperature, that one is ambient temperature, delta U would be equal to 0. If this is the case, it means that the work given to the system using impeller, it will be equal to the heat released to the environment. This is the concept of the first law of thermodynamics. That's why you can relatively easily to calculate the previous quiz. Okay. Again, as long as a cyclical change, state 1, 2, return to 1, it means that the system in a cycle condition, all the state function will be equal to 0. You can apply not only to delta U, later on it will be the same for delta H, delta S, and delta G. As long as it forms a cycle, the value would be 0. Okay, so delta G 1 to 1, delta U 1 to 1, delta H 1 to 1, delta S 1 to 1. You can make much bigger cycle, 1, 2, 3, 4, 5, and then return to 1. Because it's cycle, the value will be 0. Okay, up to this point, any question? If not, I will skip the work because we already discussed with this. Remember that work is not state function. This one is not state function. So this is an example. The starting point is from A. The final point is point in B. If you go with pathway number 1 from A to B and then return with pathway number 2, because this one is not state function, you cannot consider work AB is equal to minus work BA. This one is not applicable. Okay, but for you, internal energy, that one is correct. So UAB is equal to minus UBA because U is state function. And remember, work itself is integral P dV for closed system. Closed system. So what does it mean with integral P dV? Let's check work number 1. It means integral from A to B P dV. It means V2 minus V1. The area for work 1 is the one that I give it here in red. This is the area under the curve. Okay, this is the simple calculus. Work 2 again is integral from B to A, P dV. But the result is not the same. Why? I will give you in a different color. The area under the curve is different. Okay, based on this, which one is higher? Work number 1 using pathway number 1 or work using route number 2? Which one is higher? W1 or W2?
Number 1.
Number 1, correct. Because it is an area under the curve. That's why work 1 is not equal to work 2. This is the reason. Okay, up to this point, any question? So work 1 is higher than work 2. So please be aware, all non-state function unit, for example work, is really depend on the route or process path. But for internal energy, no matter you use route number 1 or route number 2, it will remain the same because internal energy is state function. Okay? Please raise hand if you still confused. If not, I will go for the next condition. Second one is heat. You know about this condition, heat is always flowing, heat cannot be stored. I will skip for the heat. The third one is enthalpy. This is one of the reasons why later on enthalpy is the one that normally used in process industry compared with internal energy. The main reason is simply because additional multiplication of pressure and volume. PV, this is also energy, which normally represent the energy in flow processes. So enthalpy is internal energy plus PV. Remember that internal energy absolute is very difficult to find. So no exact value because no method to validate at T equal to 0 Kelvin. So most of the time enthalpy will be used. You will find in a lot of thermodynamic textbook, they will use enthalpy instead of using internal energy. The value that you can find in appendix of the textbook in most of thermodynamics textbook normally refer to enthalpy. Okay. Now, the convection of sign is still the same. I will not discuss about this. Similarly, for general balance, you know the potential energy, you know the kinetic energy. I will not go in details about this because as a process engineer, we need to understand the concept of internal energy and enthalpy. Okay. In general energy balance that most of you should learn from heat and mass balance course. I don't know, maybe Bu Penia teach this course, if I'm not mistaken. So I'm pretty sure you're aware about this energy balance. That basically energy in minus energy out equal to accumulated energy. So I will not discuss detail regarding with this one. What I want to discuss is the concept of delta U. When you have a closed system, you can consider the pressure energy, the kinetic energy, and potential energy is equal to 0. So you will focus only on heat, work, and internal energy. So this is what happened. You remember Pak Sanggono already mentioned about this, so I will not go in details. I just give you an exercise. Let's solve this problem immediately. In process A to B, the system receives heat at 40 kilojoule. What does it mean? The sign should be positive or negative. QA. Positive 40 kilojoule or negative 40 kilojoule?
Positive, sir.
Positive 40 kilojoule, right. And receive 60 kilojoule of work. Work A, positive or negative? Come on. So we can positive again, good. 60 kilojoule. So once we have Q and W, we can have delta U A to B, which basically QA plus WA is equal to plus 100 kilojoule. Now, from B to A, following path B, the system release heat of 50 kilojoule. So QB 50 kilojoule, positive or negative?
Negative.
Negative, good. Minus 50 kilojoule. So because B is a different direction, A direction is like this, B direction is in the opposite way. So delta U BA is equal to minus delta U AB. It will be equal to minus 100 kilojoule. So work involved in B should be equal to minus 100 is equal to minus 50 plus WB. What is the value of WB? Come on. What would be the value? Minus 50 kilojoule, right? Correct me if I'm wrong. If it is correct, what is the meaning of minus 50? Receive work or release work?
Release work.
Okay, good. As simple as that. So you can also do the same thing for path C. From path C, we know that QC is equal to release heat 110 kilojoule. Positive or negative?
Negative again.
Good. 110 kilojoule. And we know that C is the same direction as B. We can use delta U BA equal to minus 100 kilojoule. Please help me to calculate WC. Minus 100 should be equal to minus 110 plus WC. So WC equal to come on guys, try it. Don't be afraid if you made a mistake.
Is it 10 kilojoules, sir?
10? No. Try again. I will help you. Delta U is equal to Q plus W. This one is 100. This one is minus 110. Ah, yeah, you're right. Sorry. So it means positive 10 kilojoule, right? So positive means the work done to the system. Yeah, you're right. Sorry, I made a mistake. Good. So please exercise more about this, because most of the time for the first midterm exam, you will have this kind of problem. But if you exercise a lot, it will be easy for you to solve it. Okay, I will skip this one, and then this is the last segment that I want to discuss. What's so called by heat capacity? Heat capacity is defined as the amount of heat, so the amount of energy that required to raise the temperature 1 degree for each unit of weight. So you need a certain amount of energy to increase the temperature. Let's say if the temperature is in Celsius, you need to how much energy that required to increase 1 degree C. If the temperature in Kelvin, do the same thing, or in Fahrenheit, do the same thing. So heat itself is, the unit of the heat is Joule. The unit of temperature is, let's say, degree C or Kelvin, degree Fahrenheit or and kind. Now, there are two types of heat capacity. The first one, if the substance is heated at a constant volume, the heat capacity will be Cv. V stands for constant volume. By definition, this is the result. du per dt at a constant volume. In other words, if we integrate this formula, you will know that delta U is equal to integral Cp delta T. Cp dt, sorry. Cv dt. Okay. So this is the basic formula for internal energy based on the concept of heat capacity in constant volume. The next one is heat capacity in constant pressure. If you check here, Cp is equal to, now instead of using internal energy. Now the formula change into enthalpy. Based on this, if we integrate, delta H would be equal to integral Cp dt. Okay, so remember one is constant pressure. That one is related with enthalpy. The previous one is constant volume, the one that related with internal energy. Now you can see the difference between internal energy and enthalpy. The different formula is related with heat capacity, one in constant volume, the other one in constant pressure. Okay, try to understand the system. Tomorrow we will discuss more about this.